Okay, so what we want to do is we want to use the Lorentz transformation to get the time dilation equation and length contraction, and then do a bunch of examples. And I want to show you how Minkowski diagrams start to work because it's really kind of neat. Okay, so we have equations. Oops. Hey, Matt. Okay. Is there anyone else coming? Let me check. Okay. Sorry, the Lorentz transformation equations. And you remember what they do. They go from the frame S, this is X and Y, to some frame moving with a constant velocity relative to this. So everything in the moving frame S prime. And this is V. So V is going to be the velocity of the S prime frame. Now, what were the transformation equations again? We said if I had a point here, I'll put it down here, I'll say X. X prime. How do I relate that to this value there, X? So X prime equals gamma. X minus VT. And then if we had a point up here, let's call it Y. So this would be Y prime. If this is moving in the X direction here, what do we say about the Y compared to this Y prime? We're the same. This is Y prime equals Y. And then we have the T prime. So if this event here occurs at some time T prime according to S prime, what does it correspond to according to S? Gamma. T minus B. X over C squared. Good. That's what we have. So these right here are the Lorentz transformation equations. And this gamma, how do we define gamma? Good. 1 minus V, yeah, V over C quantity squared. Now, let's do a couple things here. One is that quantity V over C. This often gets defined to be beta. Okay. So if we have beta here, what is the range on beta? Where can beta go from where to where? It can be zero. If it's zero, then the velocity is zero. What's the largest it can be?
0 to 1.
It can go to okay, so it's going to go up to 1. So this would be the case when V equals C. But it's not 0.
Oh.
This frame here can also go backward with the velocity. So this can go to
-1.
yeah. So this is V equals minus C. So that's the range in beta. And then as far as gamma goes, so if I plot gamma versus V, and here's C, the V over C comes in squared. What's the smallest gamma can be? Okay, let's say V gets close to C. So if V is getting close to C, I have 1 minus something close to 1. What would that be? Close to 0. If I take the square root of close to 0, I get close to 0. 1 over something close to 0 is gigantic. It's going to go off to infinity. Okay. So when V gets close to C, then this goes off to infinity, or asymptotically approaches. So we're going to find here, this function is going to go really, really up high as we get close to C. So it's the smallest this can be then. I don't know. So if I want this to be small, I want the bottom to be big. So what's the largest this bottom can be? We want the largest this can be here. And don't know.
Around 1.
Yeah, so if the velocity is 0, right, if v is 0, which you can have. But I have
Super
1
small.
minus 0, that's just 1, square root of 1 is 1, 1 over 1 is 1. So this is 1. So the smallest your gamma can be is 1. And gamma is going to stay at 1 for almost every velocity you're going to see in everyday life. So, you know, the space shuttle, when it comes into the atmosphere, is going like at 10,000 miles an hour or something. That still has a gamma of 1 for all practical purposes. Now, what happens when you start getting close to the speed of light, meaning 10% the speed of light, you start getting a little effect here, and then eventually what happens is that this really goes off like this. It's an asymptotic function. So the closer you gamma for almost everyday life, gamma is going to be 1. And then as you get closer to V, as you get closer to C, this gamma approaches infinity. That makes sense? Okay, so that's what this looks like. And so you can see for everyday life, gamma is 1. And if gamma is 1 here, this gives you x prime equals x minus vt. That's the Galilean transformation. And over here, gamma is 1. X over c squared is effectively 0. So I get t prime equals t. That's your Galilean transformation. Okay, that makes sense? So that's what we have. Now, what can we do with this? Let's get our velocity expert. Actually, let's do a couple things. Let's get the, one other thing. Suppose I want to go the other way. So this is giving me the value, this is, if I have an x and a t, this is giving me the x prime and the t prime. Suppose instead I had an x prime and a t prime, and I want x and t. How do you do this? Well, you could solve the algebra. We're going to show you the dumb way to get it. So if you want, the simple way to rewrite these expressions in terms of x and t is, okay, where the x prime and y prime, you substitute these things. So wherever you see an x prime, you put in an x. Wherever you see an x, you put an x prime, and the same with these, and the same with this. Second thing, you replace v with minus v. And if you do that, that's kind of the dumb way to get these expressions. And let's actually do this. So again, you can solve the equations and get this, but this is the easiest way to do it. Okay. So x prime goes to x. Gamma stays gamma. X prime goes to x prime. X goes x prime. And t goes to t prime. What happens with this term here? Becomes plus b. And this equation stays the same. And what does this equation become? T equals gamma. T prime plus Vx prime over c squared. Make sense? Okay, let's use these. So we're going to use both of these. Okay, so let's do the Lorentz transformation. Let's see, I can go to up here. Let's take a length contraction first. So here is S. Here's S prime. And this is going to be a rod of length L P at rest in L prime. So this length here is LP. And this rod is at rest. and S prime. The question is, what is the length of this rod here as measured in S? So what is the length of the rod of someone? Of the rod according to someone. S. Okay, so how would you do that? Okay, what's a dumb way to measure the length of an object? Let me get a length here. So here's the length. Okay, give me the dumb way to measure this. I'd measure this side here. I'd measure this side here, and what would you do those two x values?
Oh, subtract.
Subtract, right? You just measure the right end, measure the left end, subtract the two, Shazam, you got yourself a length. Now, here's the tricky part. If this is moving, how do you measure the length of a moving object? I don't know. Well, you still have to measure this side here. And you have to measure this side here and subtract them. But when do you have to measure this side here? And when do you have to measure this side here? Exactly. So if this is moving this way here, if I want if I'm at rest, I mean, I'm here. I'm seeing this object moving. If I want to measure the length of this rod, I have to measure this end and this end at the same time. So let's set that up. So I'm going to call this is going to be my left end. Call that x left prime. I'll call this my right end. This is x right prime. And what I'm going to do is I'm going to say the length of the rod. Is what? It's going to be my x right prime minus my x left prime. What is this going to be? Let's put in this fellow here. So this is going to be my gamma. This would be my x right. Is this right end, according to me, is this, right? This is my x right end. Minus VT. Now I have to subtract the left end, because I'm saying the left end is this. X left. Now, what do I know though about these two time values here? They must be the same, so they cancel. So this gives me gamma x right minus x left. And x right prime minus x left prime, what do we call that? So that'd be according to somebody at rest relative to the rod. So if I measure the length of something, and if I'm at rest relative to what I'm measuring, we call that the that's this L sub p, which we call the proper length. So this right here, we call this here the proper length. We call that LP. And this right here, that would just be the length of the rod according to somebody in S. So I'll just call this L. So this tells me that LP equals gamma L. The L is LP over gamma in Shazam. They have a very famous equation in physics. And why do we call that length contraction? What do we know about gamma? The smallest gamma can be is 1. As you get closer and closer to the speed of light, what happens to gamma? it increases. So this is small. So this is why this is called length contraction. Make sense? Okay. Bill, Matt, any questions with that?
Nope.
Okay. Now let's do the same thing from time dilation, and then we can see what we can do from there. I think this is called Lorentz contraction. This is called length or Lorentz contraction. Lorentz worked this out before Einstein, but it was this completely convoluted argument, and the physics was wrong. Einstein came along, got the exact same expression, but it's based on the correct physics. Now let's do time dilation. Okay, so what do we have here? So imagine a clock is at rest and S prime. So let's draw my little frame again. There's S, here I am. Here's my clock. I'll draw a little grandfather's clock here. So here's a little grandfather's clock. The little things on it. Here's a little pendulum for my grandfather's clock, and it goes back and forth. Here's my little clock. And this is at rest in S prime. The clock is at rest in S prime. So the question is, there's going to be some time interval here. So if I'm here, so here's an observer at rest in S prime. You're at rest in S prime, and they're going to measure a time interval. And since we're at rest relative to this clock, we're going to call it the proper time. So we're going to have something called a proper time interval. I call it delta tau. This is your proper time interval. And it is, by definition, it's going to be some t prime 2 minus some t prime. It's the difference of two times. So maybe this is 5 o'clock and maybe this is 4 o'clock. It doesn't matter. It's a time interval. In other words, maybe this is how long it takes for maybe you're in here and maybe you're drinking a cup of coffee. So this is how long it takes you to drink a cup of coffee in your restaurant. The question is, how long would a person here say it takes this person to drink their cup of coffee? Okay. Well, what are we going to do?
Oh.
Okay, so let's go through. So we want to find corresponding delta t according to an observer. In S. So we're going to call that time delta t. I'm going to call that I'm going to call that T2 minus T1. Right? That's how we're going to define it. Okay. Well, what did we say this goes as? In this case, you remember that goes as gamma T2 prime plus V, I'll call this X prime over C squared. So that's this one here. Then minus, and this we have this one here. Now we have a T1 prime here. Okay, now what do we know about these two values here? What is this clock not doing in S prime? It's not moving. So how does the X prime position of the clock here compare to the X prime position of the clock here? They're the same. So those two terms cancel. So this tells me that delta T is gamma T2 prime minus T1 prime. And this right here is my definition of my proper time interval. Boom. Time dilation. Why is it called dilation? Because this gamma here is actually 1 or larger. And so this person here. So if this person here is in a spaceship going really, really fast, drinking coffee, this person is going to say that it's taking that person a very, very, very long time to drink their coffee, depending on how fast they're going. So this is time dilation. And let's see how much you remember from 125. What was the classic experiment I gave you for this? It had to do with an elementary particle.
Observer on Earth, and then spaceship with a cat.
Never a bad thing to do. Okay, good, okay, but it's not that. But spaceships and cats, how can it be wrong? Okay, this is the actual real experiment, though, but not bad. Okay, that'll work. Okay, it had to do with basically the decay. So the classic experiment here. Showing length contraction and time dilation. Is the decay of the muon. Okay, so we have to do a little particle physics here. Okay, so here's a little background. Particle physics. Okay. This is an electron. That's an electron. It turns out that coupled with an electron is something called an electron neutrino. And so what I do here is I use the Greek symbol nu. I put a little e here. This is an electron neutrino. Now, remember in modern physics, and you even see this in chemistry, you can have a spin up electron or a spin down electron, right? The electron spin can flip like this. Is a spin up electron any different from a spin down electron?
No.
Okay. Now, I'm just going to state this, and if you take my course in particle physics, I'll work this out in extreme detail. It turns out that these particles here also have a spin, but it's something called weak isospin, and it exists in a different space called weak isospin space. And it turns out you can view these two things as basically the same particle. What they are, though, is one has a spin up in weak isospin space, the other has a spin down in weak isospin space. So these are really viewed as the same particle in weak isospin space. It doesn't really matter. That's just kind of technically what's going on. And we give these a name here. These are called leptons. Okay. Leptons comes from the Greek word leptos. Like that. And it means light. As in not heavy. These are both examples of a lepton. Okay. Now this this neutrino here, this neutrino has no electric charge. This is chargeless. Okay. It travels the speed of light. And I'm gonna give you a lie here. Here's a lie. I'm gonna say it's massless. It turns out it does have a mass, but it's small, and so I don't want to go into the implications of it having mass. It turns out something odd happens. It's called the MSW effect, but I don't want to go into it. I'm gonna cheat, and I'm gonna say it's massless. Okay, and one of the odd features here is that they barely interact with matter. These barely interact with matter. Okay. Now, nature likes this combination so much, it actually produces a heavier copy of it. And so this right here, this is called the first generation of leptons. And nature likes this combination so much, it makes it a heavier copy. So this is a heavier copy. You could say, well, why on earth does nature make a heavier copy of these? No one has any clue on this. No one has there is no understanding of why nature makes a heavier copy of this. It just knows, we just know that it does. And heavy electron is called a muon. So this is a muon. Okay, and it acts just like an electron, except it's heavier. And then correspondingly, there's a corresponding another version of a neutrino called a muon neutrino. So we call this nu. We put a little mu here. This is a muon neutrino. Okay. And again, these can be viewed as the same particle. Again, it's just what happens here is that this the one would have a spin up in isospin space, weak isospin space. The other one would have a spin down in weak isospin space, but these are the same particles in weak isospin space. Guess what happens? Okay, so this is called the second generation. Well, guess what happens? Matter likes this combination, nature likes this combination so much it makes an even heavier copy. So this is an even heavier copy. And a really, really heavy electron is called a tau. People often say tauon, or you can just, most people just say a tau. But if you want to say tauon, that's fine. Okay. And then the corresponding neutrino is then called a tau neutrino. Okay. And that's an even heavier copy. This is called the third generation. Of leptons. Okay. Again, why nature does this, no one has any understanding. And again, these are really the same particle here. It's just they differ in their spin and weak isospin space. Okay, now what can happen here? Something kind of neat. What can happen here is I'm going to plot time this way. I can have a muon. Well, let me show you what's going to happen here. We're going to find out that there's a muon here, and this muon can decay into an electron, an anti-electron neutrino. This is an antimatter version. An electron neutrino. And then a muon neutrino like that. That's what this can decay into. Let me just kind of show you how this goes. The way this works. Is I'm going to plot time this way. I can plot distance this way here. I can have a muon coming along like this. So here's my crenellated little muon. It turns out when you work through the particle physics, this can actually spit out a particle called a W minus as a negative charge. So this muon comes along here, it spits out a particle coming a mu minus. What happens here is that if this muon spits out a mu minus, it becomes a mu neutrino. This lost its negative charge. And what happens here when it spits out this particle here, it actually does a flip in weak isospin space. So this negative muon comes along, it spits out a W minus. For technical reasons, it flips its spin in weak isospin space and becomes this neutrino. And then what can happen, this can eventually decay. It can decay into basically a electron itself. And then, okay, this is just gonna sound stupid, but just deal with it. Just trust me. Into an anti-electron neutrino. Okay, this sounds like, for the next explanation, it seems like you're gonna need a beer to understand it, okay? It turns out that okay. The reason why this arrow is like this is it looks like this particle is traveling back in time. It turns out you can show that if you have negative energy going back in time, that's the same thing as antimatter going forward in time. So this really represents a particle going forward in time with positive energy. Don't worry about that. That's a very technical point. But that's what you would have here. And that's why this process here occurs. Now you could say, well, you know, thank you, but that doesn't really help me at all. Well, here's how it comes in. This process here occurs in about 2.6 microseconds. So a muon decays at about 2.6 microseconds. Okay, what's the micro?
-9.
That's a nano. This is
okay.
-6.
-6. Okay.
Okay. Now the question is, what kind of time is this? Whenever you have particle decay times, that's always a proper time. This is a proper time. Meaning what? This means that if let's say the marker here is a muon. So if I had a muon in my hand, I'm looking at my watch, and 2.6 microseconds, this reaction is going to occur. That's what that means. You know, how can we relate this to basically relativity? Here's how. Let's say here's the ground. So this is me. And this right here is the atmosphere. Okay. Let's say the atmosphere is about 10,000 kilometers. Something like that. It varies depending on where you are, but I'm just going to call it that. So this is the atmosphere. And what I'm going to do is you're going to have a cosmic ray coming this way. Okay. Cosmic rays, no one has really any clue where they come from. They think they come from something referred to as a hypernova, which is basically a supernova on steroids. And they think what happens is a proton gets accelerated to these preposterous velocities, energies, and that's what a cosmic ray is. So a cosmic ray is a very highly energetic proton. They have energies, a lot of them have energies that can't even come close to any, that no particle accelerator on Earth can even get close to these energies. Sometimes on the order of millions or billions of times more energetic. So these are highly energetic. Protons. Well, what are they going to do? They're going to have particles in the atmosphere, and when they produce, when they have the atoms in the atmosphere, they produce cosmic ray showers. So they come along, they have oxygen or nitrogen or something in the atmosphere, and you basically get this what's called a cosmic ray shower. These are a whole bunch of particles coming in. So this is the cosmic ray shower. It makes it part of the background radiation for us. One of the particles produced in this process is a muon. So one of these guys here, I'll go like this, is going to be our friend the mu. And let's say its velocity is 0.9999 c. So that means it's going at 99.99% the speed of light. Okay? So let's say all this relativity stuff is just crap, that none of this exists. So if relativity is wrong. So I'll call special relativity just SR for special relativity. So if SR is wrong, what would happen? Okay. So if you're going at 99.99% the speed of light, it's safe to call this C. So if I wanted to figure out how far this particle could travel, what would I do? So if I wanted the distance the particle could travel before decaying, I'd say it's going to be the distance is going to equal the velocity of the particle times how long it's going to have that velocity. So what would I do? I said this is approximately the speed of light, 3 times 10 to the 8th meters per second. How long does this particle live for? Well, this particle lives for 2.6 microseconds. So I put in 2.6 times 10 to the minus 6 seconds. And what would I end up with here? I'd end up with 7.8 times 10 squared meters, or 780 meters. Okay. Would you ever, if this is the case, would you ever then find muons on the surface of the Earth? No.
No.
Yeah, the atmosphere is 10 kilometers thick. So they're not even going to get through a kilometer of the atmosphere. They're all going to decay up here. We never, ever, ever find these particles down here. Fine. You do the experiment, and what do you find all over the surface of the Earth? Muons. So these muons are somehow getting down to the surface of the Earth. Now the question is, how are these particles getting down to the surface of the Earth? Okay, what was the assumption I made here in this little calculation? That special relativity is wrong. Okay, this 2.6 is a proper time. What would this person here measure? They're saying this particle move here. So does this person on the Earth measure a proper time? They measure a dilated time. Okay. And so what happens here is the person on the Earth actually measures a dilated time on the surface of the Earth. Measures a dilated time. So you have to have delta T equals gamma delta tau. And our gamma would be 1 over the square root of 1 minus V over C, quantity squared, or 1 over the square root of 1 minus 0.9999 C over C, quantity squared. And do we have any calculators out here? Woohoo! We do. Okay. I'm going to calculate this really quick. This is 70.7. I'm going to call this 70. So I'm going to call that 70. So what does that mean? It means that the person on the surface of the Earth actually measures this particle to live 70 times longer. Well, this particle lives 70 times longer. If I take this value and multiply it by 70, that basically means that that particle is going to make it to the surface of the Earth. Okay, that already supports relativity. Now, here's where it gets fun. Let's switch things up. Let's say what happens from the muon's point of view. So let's say we're going to do the following. So from the muon's point of view, okay, what happens here? So here's our 10,000 kilometers. Here. Here's a little muon. So let's put a saddle on the muon. Here's a saddle on the muon. I'm going to be a cowboy, and you need a hat for it to be a cowboy. Okay. I'm gonna basically put a saddle on my muon, and I'm gonna ride this muon through the atmosphere. Okay, so from that point of view, what do you see? So here it is, here's my little muon, I put a saddle on it, I'm looking at my watch. How long does my ride last? The proper time, right? Because if you're moving with the muon, you're gonna measure the proper time. So the cowboy measures proper time. Okay, now. Tell me if that's 10 kilometers. What kind of length is that? Is that a contracted length or a proper length, and why? Who's measuring the 10,000? You're on the earth here and you're measuring this 10,000. Are you at rest relative to what you're measuring? Yes. So this actually is a proper length. So this atmosphere here, that this, if you're down on the ground here, if you measure this length here, you're at rest relative to it. This is really a proper length. So from the muon's point of view, what do they see this atmosphere do? They think the cowboy thinks they're at rest, but that length of the atmosphere here, what do you see do? You see that length of the atmosphere move up toward you. So what would then the cowboy measure? What kind of length? A contracted length. So from the cowboy's point of view, they see the atmosphere move up toward them. This atmosphere gets contracted by a factor of gamma, in other words, a factor of 70. So from the muon's point of view, yeah, the ride doesn't last very long. 2.6 microseconds and the ride blows apart. However, they don't have to travel far because basically this length here gets contracted. And how much does it get contracted? It gets contracted by the factor of gamma, which is 70 in this case here. So they don't have far to travel. That's very cool. Does that make sense? Okay. All particle physics, basically, when you create these particles in a lab, there's some things involving quarks that live like 10 to the minus 23 seconds. Meaning if I have a particle here, some particles will decay in 10 to the minus 23 seconds. How can I study a particle that only lives for 10 to the minus 23 seconds? Now you know. What do?
You have a column.
Okay, well, in other words, if I have the particle here, the 10 to the minus 23 would be a proper time. So I'd have my little particle here, I'm looking at my watch, and 10 to the minus 23 seconds, this blows apart. How can I actually study it?
Accelerate it.
Exactly, make it go really, really fast. So what you do is that in particle accelerators, you make these particles go really, really fast. Their lifetime gets extended by a factor of gamma, and then you can actually have enough time to then study the particles, which is amazing. So all particle accelerators are designed with special relativity in place. I mean, with assuming special relativity is true. And for some reason, when somebody, okay, if you ever become a physicist and go to and teach at some university, this is what's going to happen. About once a year, maybe twice a year, somebody will contact you, either by phone, by a letter, where they have a brand new theory of physics. And it's always that special relativity is wrong or quantum mechanics is wrong. And they go through this whole litany of basically why special relativity is wrong and quantum mechanics is wrong. And, they're nonsense. The evidence for special relativity being correct is utterly phenomenal. That theory is not going anywhere. Questions? Okay, let's do a little bit more. The other thing you can see with special relativity, there's almost no assumptions. We had only two postulates. Everyone measures the speed of light to be the same, and that's based on experiment. Then the idea that if you have two observers relative to each other, moving some velocity relative to each other, that neither one can do an experiment to determine which one is moving. They were the only assumptions going into theory. And we have such minimal assumptions going into a theory. You're getting a theory that predicts so much, you really can't dismiss that theory. You have to take that theory serious. Okay. Let's do a couple more things. Let's get the velocity transformation. So how do velocities transform? Now we know this partly because we derived them. So let's go through and do it. So we have this guy. And we have this guy. You tell me how we get the velocity transformation equations. Let's see how much you remember from the other class. Okay, so we called ux prime. Remember, this is going to be the velocity of what we're studying according to somebody in the prime frame. So we call this dx prime over dt prime. What do we do with that? What do we put in for dx prime? Gamma.
X
Dx
oh,
minus
V dt.
v dt. And we divide that by
Gamma dt minus V dx over c squared.
that's right. The gammas go out here. What's the next step? We pull out a
dt.
dt. So we pull out a dt here. Now I'm doing this. Pull out one at the top and one at the bottom. That's pulling out a dt out of the top. I do the same thing out of the bottom. Look at that, they cancel here. And this is my buddy ux. So what do we get? We get ux prime equals ux minus v over 1 minus v ux over c squared. Let's try an example here. So let's say here I am, and I have a laser. I'm going to fire the laser this way, and I'm going to be in a spaceship. I'm going to come this way at half the speed of light. The question is, what is the velocity of this laser light according to someone in the spaceship? Okay, what do you do? We'll call it quits after this. What? Hey, Bill.
so do we say later that moving X prime?
Okay, so let's figure out who is S prime, who is V, who is UX, and who is UX prime. Okay, so who's S? Yeah. This is S. So who's S prime?
The
Spaceship. So what does this make this C over 2 then? Velocity of S prime is always called
Oh,
V.
you.
So this is V. And so this going to the left, it's really negative. Now, UX refers to what we're studying, according to S, and UX prime refers to what we're studying according to S prime. Okay, so this laser light here would be what? This would be the speed of the laser light according to S. So the C here is really UX. So this question over here, where it says find the velocity of this laser light here. According to somebody here, this is really asking us to find what? UX prime. So this really says find UX prime. Let's do that, and then we're done. All good for today. Okay, so we have UX prime equals. Okay. UX minus V. So I have C minus C over 2. All over 1 minus V. This V is minus C over 2. And then I have this UX here, which is C. All over C squared. So what happens? First of all, you can see that the C squareds cancel here. And so the bottom becomes 1 plus a half. And on the top here, I can pull out a C. I can pull out a C here and here. And I have a minus, became plus, so I have 1 plus a half. They cancel, and this gives me C. So we're getting the exact same thing that we got, that experiments tell us we should get. Does that make sense? Okay, what we're gonna do next time. We're done now. The next time we're gonna do the following. We're gonna have what's called a Minkowski diagram. So I'm gonna plot the time this way and X this way. So you do something weird. Instead of plotting X versus T, you put T versus X. And on the same graph, I want to plot T prime and X prime. And what I'm going to convince you of is that what we're going to do is that this is going to become the T prime axis, and this is going to become the X prime axis. So by having one point here on this graph, I can plot both X and T and X prime and T prime. Okay.
With 1 point.
With 1 point. Okay, I'll show you how that goes next time. And then we can start talking about simultaneity. And we're going to see that what's simultaneous in one frame is not simultaneous in another frame. We're going to see that perfectly with this Minkowski diagram. Okay, take care. Make sense, Phil?
I mean, towards the end, I can only hear the audio. There was no images.
Really?
Yeah.
Frozen.
Oh, yeah, it's my screen is frozen. I have no idea why that happened.
Yeah, but like I can still hear the audio, but
Okay.
without looking at the video.
Okay, let me know when that happens and I'll try to, I don't know what I can do to fix it. Hang on, let me try something. Well, if I actually come over here and then,
Well, if you can go over that last part in the next class, that'd be great.
sure, I'll do that. But let me know when that happens.
Yep.
Okay, sounds good. Take care, Bill.
Yep. You too. Goodbye.
Bye.